We're going to do a little bit of a unscientific, well, it's a slightly scientific. It's kind of like bioinformatics. You do what you can, but you're not too rigorous about it. Bake-off, so this is a non-exhaustive view of like price performance of some different parallel file system options in the context of Nextflow, right? So we'll look at a quick review of the options. We'll look at the experimental setup I said, and then show you some data and then discuss what it all means. So on AWS, but really all cloud providers, even on on-prem, you have tons of options for what your storage is, whether it's object storage, block level storage, a simple file server sitting on top of the desk, versus, real parallel file systems. And getting your storage architecture right for your data access patterns actually translates into the amount of hardware and that you can run on top of that storage, but also how long it takes for any individual process. So time is money, and sometimes money is money. So you really want to get your storage right and test along with what you're doing. All right, and we're going to focus on parallel file systems. For folks in the audience who aren't into deep IT, what really scales capacity for parallel file systems has to do more with how your clients are accessing the resources that are serving up the blocks, right? So in a simple case you have here, give me one file, one client, one file service endpoint, bring that file back. In HPC settings or more distributed settings, you're usually asking for a lot of files, and you have a lot of different access points behind the scenes. So when things get requested, those requests get distributed out to a cluster, and those clusters aggregate your request to bring that back into the client, right? This is not magic. This is literally how all file systems work at scale, and they do slightly different things to optimize for read, write performance, random read, write performance, or stream processing, whereas object stores are really tuned for stream processing. But POSIX file systems and other file systems that are high performance for HPC are tuned for very small block random read writes on what you consider a file, right? So in the case of large files like genomics, you send requests for small parts of the job that come back through it as fast as possible, and you're doing sorting, whatever, right? So this is scalable file systems. This is what you'll find on Google, on Azure, on partner systems like Weka. Like I said, I'm talking about specific AWS services because I can't really test everything. Right. So here's the. Actually, I should probably clock on time. Keep me honest on time, somebody. This is the experimental setup. We have this. Downloadable tool called Parallel Cluster that will stand up what looks like a traditional HPC cluster for you, except that the compute nodes are scalable, right? And within this YAML configuration file, you can set up volume storage. So EBS, Elastic Block Storage, is storage that's detached directly to the head node. The head node is sharing that over a single point NFS, right? And that's where I stored Conda, that's where I stored the tooling, because you really don't need that much traffic to send tooling. It's a single request to download it to the client. But for the data and the references, I stood up in Parallel Cluster, we adding in multiple file systems at different NFS endpoints. So I did these 1, 2, 3, 4, 5, 6, 7 file systems. The head node's extra large instance of Intel generation, and the compute nodes were a little bit beefier, so they were 16 CPU and 63 gigs of RAM. The thing to note about file system, though, is that 12.5 megabits per second network bandwidth that you have into these instances, right? And for some of these, you'll notice like the luster down on the bottom right here, it can sustain a 500 megabits per second throughput, right? That's provisioned. You could say, I want to be able at all times to pull that much data from that file system. That's expensive, a little bit. And then what I did is I ran the NF Core RNA-seq pipeline with some tests, but I pulled down the sample sheet and I pulled down the data onto those NFS stores, so I wasn't waiting on S3 for any of these tests, and I pulled down the data and the references, right? So, and then I ran in batches of, one, run the pipeline, just one, and then into Slurm, send that same request 3 times so that you're running 3 separate parallel pipelines, 5 and 10, right? So just keep pounding through aggregate. At one point, you had all 20 nodes all requesting data read and write back into the work dirt. So just a quick price table. Probably the product managers are going to kill me for this because these aren't completely accurate, but they're swag, right? Bioinformatics, swag. And one thing that you have to know is that Elastic File Store, because it is capacity-based scaling, the more you store in it, the faster it is scaled to grow the amount of servers in the front that will serve your request, right? So the more you store, the faster it goes. And it has these burstable capacity sustained at the small 100 gigabit level. You'll have about a read performance of 15 megabytes per second, but it can scale up until you have some credits up to 300 megabits per second, which is really quite fast. And you'll see, and what that translates into, and you'll see in these tests, is a wider range of result times for the pipeline to finish. Because as you consume credits, you gain credits, and different parts of that pipeline are going to be more I/O heavy. So really interesting, right? And then FSX for Lustre, that's traditional HPC. Those are provisioned throughput rates, so you have these set prices. We introduced OpenZFS, which was a new model that's not just for the price per gigabytes per month, but you can actually provision a megabit per second throughput, but you're only costing out at the actual pull rate that you're doing, right? Whereas you're paying for the provision on Lustre. With OpenZFS, you're paying for how much you're actually pulling. So these prices are a little bit funny. Again, I'm not too rigorous. I am a bioinformatics person. If you really want to talk to somebody who ran HPC infrastructure, Matt Vaughn, and someone there in the room, raise your hand, Matt, there he is. He's got a talk tomorrow where he actually did, the real test of I/O performance on Lustre. I took a broad view of a bunch of things. So let's show the data. These are seconds for the time. So 400 at the top end, at the 600, that's about 7-8 minutes. At the low end, it's about 4 minutes, right? And you can see that some of these have some strict outliers, like Scratch, for instance, had these outliers at the 8-minute points, and this was at essentially when you were running 10 concurrent pipelines that were all doing, all 20 nodes hitting the file system for read and write, and you were being blocked by I/O every once in a while. You'll see that EFS 1 zone had a lot of outliers at the extreme end, and this one, I don't know what happened here, right? This is sustained performance at 500 megabits per second, and all of the processes completed within 4 minutes very, very stably, except for when I was running 10 at a time. I need to redo this because I think something went wrong with what happened with my file system, or I was running something weird. So the FSX 500 megabits per second should look a lot like this guy here, except tighter. So it was a little bit faster than the 120, the default 125 megabit per second Lustre, which is also Scratch, right? And then OpenZFS, you can see, has a large variability for result times. Now, okay, so that's performance on complete pipelines. They all sort of finished around at when you weren't stressing the file system, anywhere between 4 minutes and 6 minutes, which isn't that much of a difference for the test data. But when you were really hitting it, it was the difference between 4 to 6 minutes versus 10 minutes. And again, this is just storage costs. So if you're talking about compute hitting this and having a double the amount of time to process something, depending on the price of that compute, you've just increased the cost per sample by quite a bit, right? So assuming a sustained rate for an hour, this is the cost sort of per terabyte. And again, don't take pictures because this is swag, this isn't a real thing, right? These are approximate costs. And for the cost of just running the one analysis, the average mean time to complete, it's something like 4.5 cents to run, just for the storage cost to run RNA-seq test pipeline, right? And at the low end, OpenZFS, even though it ran, sort of twice as long as Lustre, you're looking at comparable costs, right? And this is assuming a cost for OpenZFS of a constant pull rate for an hour, which isn't the case, right? It should be probably closer to 16 cents and 16 cents and 15 cents for that in OpenZFS, even though it took twice as long. Again, now you have to integrate. All right, what was the compute cost for running twice as long, right? So what's the all of this, right? So the gist is that I need to do more experimentation to be a little bit more rigorous because I didn't do a good job. But bigger compute instances with more bandwidth, right? I think that because I was running the test profile, I did limit each process to just 2 CPUs. Some processes can use a lot more threading and really pound the file system. So I'll use the biggest instances that we have with the most network throughput rate to really hammer on these file systems to tease out the difference between the higher provision bandwidth versus the lower provision bandwidth. Use bigger data sets so I have more data points, and then really, once I use those bigger data sets, really dig into the individual steps to see how they perform. So that's work that's coming. So what should you take away from this? You should test your pipelines, right? Create the test your pipelines with different architectures. The tooling's there. The automated, infrastructure as code, I believe Simon was saying, it's easy to create infrastructure on the cloud, no matter which cloud you are, to test what you should do to optimize your per sample cost. And there are some, as we've repeatedly said, volume-based unit price changes. As you grow bigger in volume, you have a different architecture that is optimized for cost in a different way than just a simple per sample cost, right? So other reasons you might want to choose other than price and performance, something like EFS actually goes across all availability zones, so you can move your data. So for instance, it's an issue getting access to some accelerated infrastructure because the AI ML folks are really taking up a lot of GPUs, and sometimes you have to go AZ hunting and even region hunting. If you have a file system that spreads your data across all AZs, that gives you more flexibility, right? And as we saw, at least for my test, EFS was close enough to parallel file systems that this might be worthwhile you investigating. And also easy backup. And the other thing about EFS and why you might want to choose this over something like FSX for Lustre is that it does intelligent tiering for you, right? So if you're not always transferring back to S3 to get your lowest cost as the source of truth, if you really want to use EFS as a source of truth, it will do that intelligent tiering for you and drop the price down from 16 cents per gigabit per month down quite a lot if you're not accessing the data. Caveat emptor, you have to know your data access patterns to see if this is worthwhile for you. And the only way to do that is to sort of test it out and run it for a few months. Why you might want to use like Lustre over anything else, especially OpenZFS, is this intelligent tiering, caching of data from S3. For instance, when you create an FSX for Lustre file system, you can say, use this S3 bucket as the source for the data. It will create a metadata file that has pointers for those files, and as soon as you start accessing it, those files become real, right? So it's doing a first pull. So any subsequent pulls will come from the POSIX file system, which is pretty cool. But that's not all. This is a Lustre feature that is being inherited. Once you start writing your data back out to that file system, it'll show up in S3 transparently, which is really nice, right? So in and of itself, that's pretty cool. That's the end of my talk. There's a lot here, right? And every cloud provider has a lot of different options. And I didn't even cover partner solutions like Weka, right? Or BGFS or other systems that are out there. So take a look, test it out, do better analysis than I did, and hit me up on Slack if you have any questions.
So thanks for the great talk. We have a question from Alex. So he's asking, can you elucidate a bit on the difference between ZFS and OpenZFS? Are there limitations in terms of features available on OpenZFS compared to the original Solaris ZFS? Or is this more coming out of licensing issues around ZFS and the features are comparable?
Yeah, that's a conversation you need to have with the storage team. I'm happy to make that introduction. It is open, it's OpenZFS as the open source product, so I'm unfortunately unable to answer that. If I can, I'll update the Slack channel.
Thank you.
Thank you.